let's talk about this Dirichlet series, sum n from 1 to infinity, and then we have the Euler-Totient function, phi of n, as our Dirichlet coefficients, albeit n to the s. So recall that phi of n is defined to be the number of integers between 1 and n such that the GCD of k and n is 1. So it's the number of integers, positive integers less than n, which are coprime to n. Now, one way you can evaluate this Dirichlet series is by knowing this identity. Phi n is equal to the sum d divides n of d times the Mobius function of n over d. And that means that this Dirichlet series we can write as being equal to the sum n from 1 to infinity, 1 over n to the s times the sum, just substituting in this expression, d divides n of d times mu n over d. And when we have a sum like this, what we can do is we can write, this is a sum d goes from 1 to infinity, and we'll have a sum m goes from 1 to infinity. So here what we're doing is we're writing n equals md, and you can check that this sum or this double sum and this double sum, they range over everything once. This is a legitimate transformation. And now what do we end up getting? Well, we have 1 over md to the s, and then here we have a d times mu of m. And here we can recognize this as a product. Maybe I'll rewrite just once for emphasis. It's the sum d from 1 to infinity of, or sum, sum m from 1 to infinity, and then here we have a d over d to the s, and here we have a mu m over m to the s. And this is going to be a sum d from 1 to infinity of 1 over d to the s minus 1, and then sum m from 1 to infinity of mu m over m to the s, and this is going to be equal to, so this term is the Riemann zeta function evaluated at s minus 1, and this term here is 1 over the Riemann zeta function at s. So what we end up getting is that the sum n from 1 to infinity of the Euler-Totient function phi, then n to the s, is equal to zeta of s minus 1 over zeta of s.